In this video, we're going to use Riemann's definition to evaluate the integral between 0 and 1 of x squared dx. It's worth noting that this is an integral that is easy to find using the fundamental theorem of calculus. The purpose of the example is not because Riemann's definition is a good way of evaluating definite integrals. Rather, the purpose of the example is to understand exactly how and what Riemann's definition for area under a curve actually is and what it is saying. And so I want to start with what Riemann's definition of the definite integral is. So Riemann's definition. And technically this is Riemann's definition of area under y is equal to f of x and over the interval between a and b. And this is indeed a signed area. What Riemann did is he said, okay, the first thing that we're going to do is we are going to add up a bunch of areas of rectangles. And then we're going to take the limit as the number of those rectangles gets big and their widths drop to 0. And if this thing is always equal to I, no matter how we choose the CKs, then we're going to say that the integral from a to b of f of x dx and the area underneath the curve is going to be equal to that limit, or in other words, equal to I. Now this is a huge, huge sea of symbols. And that's the real purpose of this example, is to kind of peel apart the multiple layers of symbols in this definition so that it makes a bit more sense, because this is probably the most difficult definition in the entire 3-semester calculus sequence. And it's important to understand this definition because understanding this definition allows us to identify when an integral might be an appropriate thing to do for solving a particular problem, particularly certain kinds of applied problems. So what I want to do now is I want to think about the context of doing this example. So I want to use Riemann's definition, and let me clean up my handwriting. So I want to use Riemann's definition to evaluate the integral between 0 and 1 of x squared dx. Now, if I just plug this stuff into the definition that we wrote on the previous page, this particular integral needs to be defined as the limit as the number of rectangles is going to get big and their widths go to 0 of the sum as k goes from 1 to n of f of ck times delta x. And we can choose the ck to be however we want. Now I am going to make the notes that our delta x is going to be b minus a divided by n, and the limits on the integral tell me what the values of a and b are. My lower endpoint is a 0, so my a is equal to 0. My upper endpoint is a 1, so my b is equal to 1. So my delta x is 1 minus 0 over n. It is simply 1 over n. The ck is anything between xk and xk minus 1, but I need to figure out what these guys are. And so that's the next thing that I'm going to do. What I want to remember is that my partition is going to look like x0 is a plus 0 times delta x, and a here, remember, is 0, so that is just going to be 0 times, and delta x, of course, is 1 over n, so this is going to be 0 times 1 over n, so that's just going to be 0. x1 is going to be a plus 1 times delta x, and that's just going to be 1 over n. x2 is going to be a plus 2 times delta x, and that's going to be 2 times 1 over n, which is going to be 2 over n. In general, xk minus 1 is going to be a plus k minus 1 times delta x's, which will wind up in the context of our problem being k minus 1 over n. And xk is going to be a plus k times delta x, which in the context of our problem is going to be k over n. And these xk's keep piling up until we finally get down to xn, which will be a plus n times delta x, and that will be n over n, which is 1, which is our b value. Now I want to kind of look at all of the stuff that we've got here, and I want to realize that these two things tell me where my ck is going to have to be trapped by. Looking at the red boxed stuff, what I know now is I know that we're going to have k minus 1 over n is going to have to be less than or equal to ck, is going to have to be less than or equal to k over n. Now, the beauty of this definition is that we can pick ck however we want, as long as it lies inside the kth subinterval. So as long as ck lies between these two numbers, it does not matter how I pick ck. Notationally, right Riemann sums are the easiest to deal with, so we will choose to pick a right Riemann sum to stick inside our definition. So we will choose a right Riemann sum for sticking inside our definition of the definite integral. And our definite integral is not just any old definite integral. Our definite integral is the definite integral between 0 and 1 of x squared dx. And so what this means is that we are going to choose ck to be the right-hand endpoint of my kth subinterval. And the right-hand endpoint, of course, would be this one. So once I know how I'm going to choose ck, the next part of the problem becomes plugging stuff in. So at this point, we know ck is going to be k over n, and we know delta x is 1 over n, and we know that f of x is equal to x squared. So the integral between 0 and 1 of x squared dx is going to be the limit as n gets big, and the delta x is going to shrink to 0, of the sum as k goes from 1 to n of f of ck times delta x, but delta x is known to be 1 over n. So just to kind of keep track about what things are, ck is k over n, and delta x is 1 over n. So ck is k over n, and delta x is 1 over n. Well, once I do that, f of x is x squared, so I am now looking at the limit as n gets big and delta x shrinks to 0, of the summation as k goes from 1 to n of k squared over n squared times that 1 over n. Now, the k is what's varying, and I'm going to kind of rewrite this very slightly. I can rewrite this limit as the limit as n gets big and the delta x's are going to 0. And notice that the delta x's, because they're 1 over n, are going to go to 0. What I've got now is the summation as k goes from 1 to n of k squared. Let me make that notation very clear. K squared times 1 over n cubed, because I have an n squared here, times an n there, and n squared times n is equal to n cubed. And the other thing is that this 1 over n cubed is a constant as far as the summation is concerned. K is the counter variable, so it can be pulled outside the summation sign, and we are now left with the limit as n gets big and delta x goes to 0 of 1 over n cubed times the sum as k goes from 1 to n of k squared. And what I want to do is I want to think about that summation. That summation was on the list of things that we know closed formulas for. And so I would like you to stop the video and think about if you can figure out what the closed form for this particular integral, rather for this particular sum actually is. And I'm going to do that sum on the next page. We've gotten down to the point where we know that the integral between 0 and 1 of x squared dx is the limit as n gets big and delta x is shrinking to 0 of 1 over n cubed times the sum as k goes from 1 to n of k squared. But that is a summation formula that we happen to have a closed form for. So we are now looking at the limit as n gets big and delta x goes to 0 of 1 over n cubed times, and this is from learning module number 17, if I recall correctly. This closed form is n times n plus 1 times 2n plus 1, all divided by 6. And now we have to figure out the limit. Now, that means we're going to have to evaluate this particular expression up here. However, I can save myself a little bit of time by realizing that n is going to cancel with one of them, leaving me with an n squared down here. So what I've got the next step algebraically is the limit as n gets big of 1 over n squared. Let me make that square better. 1 over n squared times n plus 1 times 2n plus 1. And trying to multiply that out is not that difficult, so let's get that done. We're looking at the limit as n gets big of 1 over n squared times, and this is just distributing it out, or many high school students in this country will say foiling it out. But what we've got is 2n squared, and then I've got 2n there plus 1 more n, so we have 3n plus a 1 from the 1 times 1. And this is now very easy to, I've lost that 6, so let me put that 6 back in here. So this 6 here got lost. Let me point that out. I lost that 6 when I came down here, so I need to put the 6 there. And now I'm going to put the 6 here as well. So that's where that 6 is coming from. So we're now looking at the limit as n gets big of, let's see, I'm going to rewrite this one more time before breaking it apart. I've got 2n squared plus 3n plus 1, And the bottom is now 6n squared. Let me make my notation clear. Now, to evaluate this kind of a limit, it is enough to think about breaking the fraction up at these two plus signs. So we are now looking at the limit as n gets big of 2n squared over 6n squared plus 3n plus 1 over 6n squared. And let me clean up the algebra, and then it's easy to figure out where the limit is going to go to. In this first fraction, the n squareds cancel out. In this second one, the n cancels one of the squares. And so what I'm really looking at in terms of the limit is the limit as n gets big of 2 over 6 plus 3 over 6n plus 1 over 6n squared. Now, as n is getting bigger and bigger and bigger, 3 over 6n is dropping to 0, and 1 over 6n squared is dropping to 0. So when I pass to the limit, I get 2/6 or 1/3, which is exactly what we were expecting. So the net result of this is that we have now shown that the integral between 0 and 1 of x squared dx is equal to 1/3 by using Riemann's definition. So by using Riemann's definition instead of the fundamental theorem of calculus. You will have some problems in homework where you will have to use Riemann's definition, because I do want you to understand this definition.